Welcome. In this video, we're going to talk about functions and how we can write our own functions to harness the true power of programming. First, let's take a look at where we've come in the challenge so far. In day one, we got started with a very simple, quintessential Hello World program. Then in day two, we learned about variables and using the Turtle library. In day three, we explored for loops. And in today, day four, we're going to work on writing our own functions. And finally, tomorrow in day 5, we're going to put everything we've learned together. Now let's look a little more deeply into how we can really start to scale our programming capabilities by creating our very own functions. So why are we talking about functions anyways? Why are they so important? Well, first, a function allows us to name a group of code statements, which makes our programs easier to read, test, and debug. Since the majority of development time can be spent debugging, any savings we can get there in terms of time are super important. So how does it help us do that? How does it help us simplify testing and debugging? Well, it allows us to focus our attention on one function at a time before we try and test and debug the whole program. This is kind of like how you might focus on cleaning one room of your home instead of all the rooms at the same time. I mean, can you imagine someone trying to mop, broom, and vacuum all at the same time? It would be very challenging. You can really only do one thing well in one moment at a time. And so the functions allow us to focus our attention to break down our problem into manageable, bite-sized chunks that are easier for us to work with. And that's how it helps us test and debug faster. Functions also help us reuse our code, which is one of the main reasons we write code and programs in the first place, is so that they can be reused over and over and over again. And finally, functions help us eliminate repetitive code, which is also a really important component of programming. When we go to reuse our programs, or if we want to edit them later, it means we only have to make changes in one well-defined place. And this is really helpful because if we've been copying and pasting our code all over our program, and we have a bug in one of those, we probably have a bug in all of them. And so we'd have to go back through and remember to make changes in all of those different locations. By putting that repeated code in a function instead of copying and pasting, then it's going to simplify our development. It's going to simplify our lives for creating working pieces of code. All right, so now let's look at an example function. We're going to start with a really simple function called add. And what's going to come into this function are going to be two parameters, x and y. These are the values that we're going to pass into the function. And then what's going to come out of our function is the result, or the sum of x and y. More formally, the parameters coming in are x and y, and what comes out is called the returned result. In this case, it's going to be our sum. So let's take a look at what our Python code might look like to call such a function. So here's an example line of code that calls the add function that we've been describing. It starts with the function name here on the right-hand side of the equal sign. And then in parentheses after the function name are our parameters. In this case, in the call of the function, these are the actual values that we are going to pass our function. It's not x and y, it's 5 and 7, the actual numbers that we want to add together. Then once the function is executed, the result gets stored in our sum variable, and this is the returned result. And the equal sign is what's doing that assignment for us. So now let's look at how we might define such a function. And again, this is in Python. So here we have a simple function definition for the add function. And let's talk about each component in turn. First, we start off with the Python keyword def. This tells Python that we want to define a function. And this first line is known as the function header or signature. Then we have the function's name, add, followed by parentheses, and we have x and y. These are the parameter variable names. So these are variables we're creating, and these variables only exist in this one function. That's what's called their scope. After that, every line of our function is going to be indented. Python is really persnickety about indentation. This particular function is very simple, and so I just have one line, but if we had multiple lines, all of those lines would need to be indented as well. Return is the keyword that we use in most programming languages to give a result from a function and to exit that function, and it's going to immediately exit that function. And then the value that we're going to return comes after that keyword, and that's our result of adding x plus y together, which is what our add function is intended to do. Now let's put our call and our function together to see how a program works. Now in this program, I'm also going to represent what's happening in memory, or RAM, while our program is running, and that's indicated in the green box. So I'd like you to take a moment and think for yourself, where does our execution begin? What do you think is the first line of code that's going to be executed? If you said the add line, where sum equals add 5, 7, then you are correct. While the function definition happens earlier in the program, from a user's perspective, you could put 100 function definitions in your program, but if you never call them, it's like they don't exist. So our execution from the user's perspective actually begins below all the function definitions, where the functions are actually called. Let's look at how our execution flows through the program. So when the add function is called, the actual values of 5 and 7 get copied into our parameter variables x and y. And this is happening behind the scene, which is why function calling can be a little bit challenging for new programmers, because all of a sudden you're not flowing through your function one line after another. Things are bouncing around and happening behind the scenes. You need to understand what's called the semantics of what's happening there. So we've copied the values of 5 and 7 into x and y, and we can also see they're represented in memory in our diagram. Then we're going to execute the two statements that are in the function's body, both of which are indented. And then when the add function is finished, it returns the sum and assigns it to our sum variable. Okay, and then finally, we're going to print our sum, and that's where the execution ends. So what I'd like to do is summarize all of these different components and the flow that we saw. So first we started with our call to add 5, 7, which was then passed to our function definition. And so those variables x and y get the values 5 and 7. We printed, we returned x plus y, and then we assigned that result to our sum. And finally, we then printed it. And what I really want to draw your attention to here is how the flow of execution from statement to statement is nonlinear. It's bouncing around. It's going from here, it's going to there. And so once you start building well-written programs that are making use of loops and functions, things don't just follow in a straight line anymore. And so it's important to understand the mechanics of what's happening behind the scenes so that you can understand what your programs are doing. And finally, what I'd like to leave you with is a question I see all the time from beginner programmers. What's the difference between returning and printing? Let's contrast the add function we've been working with here, which returns the result x plus y, with a version of add that only prints the result. The function on the right with print will only ever display to the screen. And while that might be what we want to do right now, it might not be what we always want to do with our sum. And so return allows us to give our result back to the location of the call so that we can then assign it to a variable, pass it as a parameter and use it inside another function, or print it. And so return allows us to use our function in a way that can be used in many more situations than just printing. Now that we understand the mechanics of how a function and a function call work, let's look at how we can harness this power for ourselves by writing our own functions with a template. So the template that we're working from in Python to write a function is def function name, and in parentheses, any parameter names. And there doesn't have to be any parameters, but if there are, all their names should be specified, separated by commas. And then after a colon, we have the function's body, which is its implementation, the reusable code that we're going to execute when the function is called. And all of these lines of code should be indented. So what are the steps? What I'm going to do is go over the 7 steps to writing a function, and then we'll walk through them with an example. So our first step is to write the code, not a function, for one concrete example and test it out. So just as we did with the triangle, we're going to write out the code and then test it. Forgetting about the function for a moment, we're just going to get some code working that does what we want it to do. It doesn't have to be reusable yet. Then in step 2, we're going to look for any repeated values that we see in our code and replace those values with variables. In step 3, we'll then identify any parameters. So these will be variables or values that we expect to change every time our function is called. Those will become our parameters. In step 4, we're going to write the function signature. So that's the first line of the function that begins with def. That includes its name and parameters. In step 5, we're going to write the function's body. And we're going to substitute in parameter names for variables if they're different. But if we do this process right, when we replace repeated values with variables, hopefully we'll be choosing names that also make sense as parameter names. And so we won't have to actually do any substitution here. Next, in step 6, we're going to test the function just once for our example that we started with in step 1. And ideally, the output should be the same. Remember, good implementation process means that we're making as few changes as possible before running and testing our code again. So we want to implement our function and not change anything but the design of the code, going from no function to a function, and make sure that the output is the same. Finally, in step 7, we want to test some more, because the true test of a function is if you can substitute in different parameters in the same program and you get different output. So we want to call our function 2 or 3 more times in the same run. So let's unpack these steps a bit by using our example triangle code from day 3 of the challenge. So the first step is to write the code for one example and test. In day 2 of the challenge, we actually did just that. We implemented the triangle code, there's no function here, and we also completed step 2 where we replaced any repeated values with variables. And here we introduced the size variable that we then used in our turtle.forward call. In step 3, we identify parameters. So which variables do we think will change with every call? And since our goal is to create triangles of different sizes, the size variable that we've already used is likely to make a good parameter. Let's also double check the other values that are used to draw a triangle, just to double check our work. Should any of them change? Well, a triangle always has 3 sides by definition. So range 3, probably going to stay the same for every triangle we draw. And in this case, we are drawing what's called equilateral triangles. We are not trying to draw every triangle. We're trying to draw a very specific triangle. And in this case, every triangle we draw is going to have an internal angle of 120. So that number is not going to need to change either. So we've double checked our work and we've confirmed that size is the only parameter. Awesome. So let's move on to the next step. So in step 4, we're going to write the function signature, which is our name and parameters. So in this case, we are going to use the name triangle because that describes what we're creating. And the size variable that we identified in the previous step will become our parameter. Next, we need to write the function's body. And if needed, substitute parameter names for variables. Because our code was already written with size as a variable, we won't need to do that here. We can literally copy and paste in. This is one instance where copying and pasting is okay. Our code from before into our function and have it work properly. So our next step, 6, is to test. And we want to make sure that our output when calling this function is the same as before. So let's try it out. So here I've implemented the triangle function we just described, and I've called it down below. So I've called our triangle with size 100. And if you recall the mechanics of how a function call works, that 100 value is going to get substituted in for the size parameter, just like it did before in our other code. And what we can see is success. The triangle is exactly the same as before. So we've tested our one example. So looking at this code on the left, let's compare this with our original example code. What are the differences between our function implementation and our code without the function? So first we have the test function call. We're calling triangle 100. And then we've also added a function signature at the top, def triangle size. Compare this with the code on the right because the fry and range part is identical. On the right, we simply have a declaration of the size variable and we're setting it equal to 100. And this is the variable that became our function parameter. So on the right, if we wanted to draw multiple triangles, all we have is the ability to copy and paste, which we know is a no-no. It's not dry. But on the left, because we've introduced a function signature, now we can call the function, and we can do it many times, and it will be really, really easy. So what we'd like to do in the final step 7 is to test some more, because the true test of a function is calling it with different parameters in the same program. So let's test calling out our triangle a couple more times. So here I have gone ahead and implemented these test function calls. Now what you might notice is that in between my triangle function calls, I've interspersed some calls to back. What I've done is implemented a helper function back to move my turtle back so that my triangles don't overlap. I chose backward over forward because I found when I moved my turtle forward, I was extending beyond the default trinket canvas size and my turtle was getting cut off. So this is the solution that I found here. And what we can see is that we are successful. We've made 3 calls to the same function and we have 3 different triangles in our program. The other thing I'd like to draw your attention to is that my test function calls on lines 14 through 18 are below all of my imports and function definitions. This is a widely accepted best practice for organizing Python programs. So are you ready to try it out? Here we have the code from day 3. Please load that up. And what we're going to do in today's activity is to implement the triangle example as a function, as well as practice creating a brand new function, square. So for details, please see the worksheet along with a video solution. And I can't wait to see you in day 5 where we put all of our learning so far together.